Hello, calculus students. Miss Deer back on the mic today. We are going back to something we actually talked a little bit about in chapter 11, which is parametric equations. And remember that we use these for lines in 3 space. And the idea is that you have a set of equations, x, y, z, or just x, y, that are all functions of the same variable. So if you have a function like y equals x squared, which makes a parabola, then you can turn this into parametric equations. The easiest way is just to let x equal t, y equals t squared. So this will still sketch the same function, but it will sketch it with orientation. So as x gets positive, your parabola will move in this direction. And it also allows us to make functions out of things that were not functions before, like circles, ellipses, hyperbolas. Something like, let's say x equals t squared minus 4 and y equals t. So now as t gets bigger, y gets bigger, and your x values will travel along this parabola that's actually tilted sideways. So we can actually get out our calculator and use a new mode on our calculator, which is exciting. So if you turn on your calculator, which I'm sure is in radians and in function mode, and if you hit mode, you will notice, oh good, I'm in radians, I'm in function mode, and right next to it, it says parametric. So if you actually choose parametric mode, nothing changes in your home screen. But in your y equals, you now have x is a function of t and y is a function of t. And this button here, xt theta n, which would give us x's in function mode, will now kick out t values. So if we let x equal t squared minus 4 and y equals t, it will sketch this sideways parabola with orientation. And we can actually restrict it. Typically t, like you learned with related rates, stands for time. So your calculator will default to having your t values go from 0 to wherever. But if you hit window, you can now alter your t values. So instead of starting at 0, mine start at -3 and go to +3. So that means that my y values will go from -3 to +3. So are you ready for the graph? So we now have a sideways parabola. That is, it's actually a function. So because I now have, so my function looks like this. And it has orientation, so we're just gonna, instead of putting arrows on both ends like we did when we were working with functions, we're now just gonna put one arrow along the curve. So if I want to apply rules of calculus to this, and I want to find the slope of a point, well, first we need to figure out how we find a point. Remember that like we did with linear functions, any time you plug in one t value to both x and y, you'll get, in this case, an ordered pair. So if t equals 2, this will kick out the point 0, 2, which is right here. And again, if we were just plugging in x values, this is not a function because you have 2 of the same x value, of course, you have 2 y values corresponding to the same x value. But we only plugged in one unique t value and we got out one unique ordered pair, so this is now a function. So if I want to find dy dx, this is change in y over change in x. Well, y is changing with t and x is changing with t. So if I think about this as dy dt over dx dt, this ratio gives me the change in y over the change in x. So looking at these two functions, to find the slope in terms of this plane, I would have dy dt, which is 1 over dx dt, which is 2t. So remember, your slope is itself a function of t. For different t values, you'll get different values of the slope. So for our t value we picked here was 2. So if I plug in t equals 2, I get my slope is 1/4. So here's my line right here with a slope of 1/4. And so let's think about how this is going to work finding the second derivative. So finding my second derivative, I need to find the derivative with respect to x of this derivative. But everything here is in terms of t. So what I really need to do is the derivative with respect, so just like here, I did change in y over change in x. Here, I'm gonna need change in slope over change in x. Because remember, this is our concavity. This is the rate of change of the derivative. So I wanna know how the derivative is changing with respect to t as x changes. So this is going to be the derivative with respect to t of dy dx over dx dt. So this is always how we're going to find the second derivative. In this example right here, my second derivative is, well, the derivative with respect to t of my derivative, which is -1 over 2t squared, all over dx dt, which is still 2t. So my second derivative is -1 over 4t cubed. If I then, again, plug in my t value here, which is 2, I get -1 over, 8 times 4 is 32, which is a negative number, which is concave down, which goes along with what we know about this graph. So let's do another example where we have, let's say x is 3t and y is sine of t. So if I wanted to sketch a graph on that, I certainly could on my calculator. First we'll do the math, then we'll go ahead and put that in there. So let's find the function for the derivative. So the function for the derivative, dy dx, is going to be the ratio of dy dt over dx dt. So this is going to be cosine t over 3. Excuse me, to find the second derivative, it's going to be the derivative of the derivative with respect to t over dx dt. So it's going to be the derivative of this term, which is negative, which is 1/3 times the derivative of cosine t, all over dx dt, which is still 3. Cleaning up my complex fraction, I get negative sine t over 9. So when t equals pi halves, I can plug that into the originals. That will give me a point on this graph. 3 times pi over 2. Y is sine of pi over 2. 1. When I want to find the slope of the graph at this point, I could plug t equals pi halves into my derivative. Cosine of pi halves is 0. So if I have a slope of 0 that goes through this point, the equation of my tangent line would be y equals 1. I could also find my second derivative, which would be negative sine of pi halves, so -1 over 9, which tells me that this graph would be concave down. So sketching on my batteries, hopefully they hold out. So sketching this on my calculator, I'm going to put in x equals 3t, y equals sine of t. For my window, I probably want to get a whole cycle of this. So let's say t goes from 0 to 2 pi. And maybe for my, for my window, well, I don't know, we can just try it with a 10 by 10 for now. Woo! There it is. All right, so we've worked with parametric equations. We understand the beauty of parametric equations. Let's go to arc length. I think I've said before, arc length is probably the thing that we're going to have the most equations for in this class. If I'm looking at arc length, in terms of the Cartesian plane, we took the integral of the square root of 1 plus dy dx squared dx. Well, if I want to change this, if I'm looking at parametric equations, so that instead of being in terms of x, I'm in terms of t, I'm going to want to change this variable. I'm going to multiply by dt over dt. So my arc length is going to turn into the square root of 1 plus dy dt over dx dt squared times dx dt dt. And if I want to leave this guy outside and move this guy inside the radical, I need to square it. And remember, it's going to go to this term and it's going to this term. So I get the square root of dx dt squared plus dy dt squared times dx dt squared over dx dt squared. These two are going to cancel each other out. So I get dy, over dt squared dt. Notice, this is actually what we used to derive this formula back when we were living nicely in 2-space. This is change in x squared plus change in y squared. We're adding up infinitely many, infinitely small Pythagorean theorems.